do something with Eric too, where we just make,
Mm-hmm.
we try to make dots or samples as small as possible, and then use his fancy centrifugation
Mm-hmm.
to isolate the very smallest one. That would be something fairly simple. That could be done within a month.
Yeah, it is interesting. Hmm. Did you? I was asking it before, but I'm wiping off memories each night. So, or is there anything interesting going on for manganese doped that I'm not aware of?
Um, I think he sent you the figures
Mm-hmm.
that he had up to this point. I don't know if you looked at them,
I did, and
but the most,
uh-huh.
I was going to say, the most interesting thing that we could potentially do is that we made two versions, doped and undoped. And with the undoped, like their band gaps follow the usual expectations,
Mm-hmm.
whereas small samples, larger gap, and then as they get larger, it plateaus.
Uh-huh.
But with the doped, the the band gap never plateaus to the like the bulk limit.
Mm-hmm.
And for those same samples, we kind of think that those are the ones that are like highly doped
Mm-hmm.
or high concentration of dopants. So it could be producing like an artificial confinement.
Mm-hmm.
So potentially with a model, if we use one of the big big models that we have for the Kuno or did for the Kuno group,
Mm-hmm.
and just make like a small, make like a quarter of it, replace the lead with manganese.
Mm-hmm. Um, if we do calculations for the manganese dope, I remember in your paper so many years ago, the oscillator strength for DD transitions was vanishing or qualitatively below experimental range. Do you see any quick fix for it rather than doing multi-reference calculations?
So
I know that.
I guess the low,
Yes, yes, I'm listening.
I think the low oscillator strength is expected. So I don't think that's the problem. The problem, but the way I saw it, the main problem we had is that when we tried to model the photoluminescence,
Uh-huh.
is that the band gap of the dopant was wider than we would want.
Okay, and
So that,
was it fixed if one uses chlorines instead of bromines? Hmm. Okay.
and I've been thinking of, well, I thought about it a little bit, and I think the main problem is that we use the ground state
Mm-hmm.
energy levels, whereas the manganese dopant is going to be in an excited state. And so that's like small changes in spin produce big changes in the energy levels.
Mm-hmm.
And so I did just some quick calculations on some of the models, and I did find for one of them, if I put it into, if I constrain the spins to 3/2, that I was able to see like the like a good energy, good alignment of the orbitals.
Mm-hmm.
So it looks like there was a D inside, like the 2D levels we would want inside the gap.
Did you try the constraint DFT for the magnetic moment, as you described right now, as a mean to evaluate the transition energy of the optical transition? Like if you take like configuration with one spin polarization, then you flip a spin and find total energy, and then subtract these two energies and tell that, okay, it will be energy of photo excitation. We did it in past with G Yao in South Dakota, and for lanthanides, which are much more exotic and challenging than manganese, this approach gave like very good, I wouldn't say excellent, but very good agreement with experiment. Like the error was 5%, which is a rare for DFT.
I think I know we computed single point calculations for various spin multiplicities. So we have the data. I would have to look at it. But I think it was more, and you said total energy, right?
Yes, total energy in different spin configurations. If the
I remember it was like, I remember it was on like the at least 3 EV. It was on that energy range.
Interesting. Another thing, right now, I don't know if we came to useful conclusions before. I have wiped off any memories and trying brainstorming and you. There is another thing. When I was looking on the trajectories, the local environment of manganese was dynamically changing from orthogonal from the 6 to 4 neighbors, from octahedral to tetrahedral. So maybe the unfavorable, not incorrect value of the excitation energy, because we didn't allow manganese to relax long enough and for nearby bromines to take minimal configuration. And it is known that for tetrahedral the D splitting is less, and it will be more in the optical gap will be smaller.
Yeah, that could be something to track or look into.
I want to ask something. If when you were reading the literature, did you find analogy? Like, did anyone was trying to use elements below manganese, like technetium or rhenium, to dope perovskites?
I've never seen that. I remember looking into it when Braden was asking questions about it. And there are some calculations for those, but yeah, I think one of the problems with those elements is that they're radioactive. So that might have dissuade some people from working with them
Okay.
for dope instead.
Okay. So maybe the ligand field coordination will work positively. Some time ago we kind of stopped this direction because of these objective difficulties, but if there are, well, since there are experimental results, maybe it could be a possibility to revise it.
Mm-hmm. I'm trying to see if on the computer that I'm using for these videos, I have one of the figures I was talking about.
Pardon me? Just please repeat. I was disfocused.
I'm trying to see if on the computer I'm using, I have one of the figures I was mentioning earlier.
Uh-huh.
Mm-hmm. No, it doesn't look like it.
Okay. Okay.
But I know at one point I was able to get DFT to get the ordering of the d orbitals that we were expecting.
Mm-hmm.
That would give photoluminescence. I'll have to dig around for that and see if I can find it.
Okay. I want to be objective and do not want to be enslaved by my own thoughts. But I'm kind of circling around this thought again and again, because in the manganese doping is used in zinc oxide and cadmium selenide as a replacement doping, and there it gives signals in the visible spectrum, and there the coordination is tetrahedral.
Mm-hmm.
On one hand. On another hand, perovskite is known to be quite soft and flexible, and conversion to a tetrahedral would be another big surprise. Maybe one can intentionally distort nearby atoms to tetrahedral coordination to prompt system direction of optimization, because otherwise we may need to wait too long until system takes it.
Mm-hmm. And then it can just donate the other two halides to leads that are,
or to the surface.
right. Yeah, to like the exterior of where the dopant is.
Yes, yes. I remember I was putting a video of this transformation on YouTube. Just I will not find it as quick as we speak. But I remember showing it on group meeting and on some conference, and I'll share it if I find it again. And there it looks like system is coming naturally to the tetrahedral coordination around manganese. Okay, do you have any other subjects to cover?
Nothing pressing at the moment.
Okay. Yeah, if you find out that we need to talk, we don't need to wait for the group meeting. Right now, all our schedules are, at least my schedule is more flexible. I need to do the same or maybe more things in time, but they are mostly based on accomplishment rather than being done at a certain time. So we can check liberally, uh, just choosing time.
Yeah, I'll keep that in mind.
Okay, then I suggest we complete the session and we disconnect.
Okay,
Okay, very good.
sounds like a plan.
Yeah.
Bye, Dimitri.
Bye, Aaron. Nice talking to you.
You as well.